the recording is started. So as I just said, today we are going to talk about the energy converters on board of an electric vehicle or hybrid electric vehicle. And we have learned already the energy storage. And as we just talked about the energy storages, we know that we are going to have the battery as the energy storage, the fuel tank as the energy storage, or supercaps, short-term energy storage, they can be used. Or if you want to store H2, the hydrogen, then we need to have either a pressurized tank or liquefied hydrogen, or we can also use metal hydrates if you like. So we know the power converters, now power energy storage devices. Now we are going to talk about the power converters, and basically I'm going to talk about the internal combustion engine shortly, then hydrogen fuel cell, or just the fuel cell. In Turkish, it is called the yakıt hücresi. In third place, we are going to briefly talk about electric machines, and later on electrical to electrical converters, then mechanical to mechanical converters. So I use power converters, energy converters. Just I use both words, power, energy, but anyway, they are going to be the same. So before we start, I just want to mention that earlier we have learned the battery systems like lithium-ion battery cells, lithium-ion battery systems, and we said that actually they are storage devices. But it is maybe important to note that these are, can I do? Okay. So this battery, these are, I was playing with it, so maybe I did. So the batteries are not just the storage elements, but they also have power conversion units. The storage is the active material in the anode or cathode, because it's going to move from one side to the other. So the storage is the amount of the active material. And the power conversion is the speed of the motion of this active material or the ions from one side or the other side. So the power conversion is related to the motion of the ions plus ions and anyways, ions and electrons. So the active material, if you increase the active material in a battery, it means that we are going to have a higher energy battery. So the energy can be increased of the battery. And as you also do it in your projects, and as we discussed many times, the batteries also need to have some high power. How fast can we discharge them and how fast can we charge them? Power ratings. So the energy ratings is related to how much active material is stored within the battery, and the power rating is related to how fast the energy conversion can take place within the battery. So therefore, actually, the batteries are both storage elements plus the power conversion elements. So it is good to know, because the stored energy is the chemical form and the output is the electrical form. So therefore, just have a heads up, the battery can be also listed here as the power converters. But since we already discussed its characteristics earlier, so I'm not going to discuss it. So first, we will start with the internal combustion engine. We have learned this term many times throughout this lecture. And actually, this is something I think you know, or you heard a lot. So this is actually a part of our regular lives, the internal combustion engines. So the name says that there is going to be a combustion. The combustion is going to be inside, and it is going to create some motion. So the combustion, actually the terminology means that if you combine something with the oxygen, then it is the combustion. And from the combustion, we expect to have some force, then some explosion and some force. And from the force, we are going to have the mechanical power. So it means that actually we are going to burn the fuel. And once the fuel is burned, then we are going to have some force, and we are going to use this force. This is what the name suggests, the combustion internal engine. In most of the case, we use the four-stroke gasoline engine. So we are not going to talk about many types of the internal combustion engines, but let's talk about the four-stroke ones. These are the most common ones. The four-stroke means that it has two phases. These engines are going to have four phases. So four-stroke. So they are going to have work in four separate phases. Let's call it like that. So these combustion engines, first of all, they have a piston, or this is called the cylinder. It looks like a cylinder. Maybe it will come in the next slide. So there are, which you don't see, there are cylinders. Maybe in the others, no, I don't put any cylinders. So this housing inside, they are the cylinders. And in the cylinders, we are going to have pistons. Pistons are going to move up and down. And these pistons are connected to a crankshaft. And this linear motion of the pistons, so the pistons are going to move in the linear manner, and the shaft is going to rotate. So from this assembly, this linear motion is going to be converted into the rotating motion, and this is going to be our crankshaft. So here we are going to have rotating motion. This is the linear motion. And in the cylinders, in the four different strokes, first we are going to get the fuel inside, or the mixture of the fuel and the air. So not just the fuel. So you know that we have the, we always use the mix of the fuel plus the air. And in the first phase, in the first stroke, let's call it the first stroke, we are going to take the mixture of the fuel and the air inside the cylinder. And we are going to have it like a suction. So it is called here the induction. So this piston is going to be moved downward. So it is going to move downward. So here we are going to have a negative pressure, and this part is going to be open. This plug inlet valve is going to be open, and the fuel is going to come in. Fuel is taken in, let's say it like that. And this is done by the external force. So it can be you just need to move the piston downward, so, and open the inlet, so the fuel goes into the cylinder. So here we have the fuel. In the second stroke, the external force, which can be again U or some other force, has to move the piston upwards, so that here the valves are closed. Valves closed. And this is moving upward. So it means that the fuel inside is going to be compressed. We are just compressing the fuel. So we are increasing its pressure. And after the fuel is compressed, so I think this is the ignition part here. Yeah, fuel injector, spark plug. So this is where we are going to apply the ignition. Exactly once the fuel is compressed enough, we are going to ignite it if it is a gasoline engine. And if it's a diesel engine, you don't need the ignition. It will just explode, or combustion happens just once you reach a high pressure. And here you ignite the fuel. And due to this ignition, for the first time, there will be some force generated by this explosion or by this combustion. So this F was external. We had to suck the fuel with an external force. Then we had to compress it with an external force. But for the first time, this part, for the first time, we have generated some force. So there was the explosion. So this F was generated by the combustion, internal combustion engine. So after the ignition here, we are going to have a downward force. The cylinder area or volume wants to increase because of the explosion in this region in the cylinder. Then once the explosion is done, it is perfect. We need to push the piston upwards. that, we need to push the piston upwards so that the exhaust gas, the remaining of after the explosion, can be removed. So F external is going to push the piston upwards. So the valve, which is your exhaust valve, this valve will be open, and the gas will go to outside. And this is going to be fourth stroke. And this is the third stroke. So because of, and after the fourth stroke, as you can guess, this is going to repeat, because now the inside of the cylinder is empty and the induction will start, or the suction part will start. The fuel will go into the cylinder, then we need to compress it, then ignition, then after that there will be an expansion phase because of the combustion. Just after the combustion, then we need to get rid of the exhaust. So, and this is going to repeat itself after and after each other. So that kind of an operation is called the four-stroke operation. And as you can see, actually, the engine is just creating torque during this time, during the third phase of the whole process. In all the other phases, the system needs some external force. Otherwise, we cannot make the internal combustion engine operate. So actually, therefore, the internal combustion engines are not capable of self-starting. So if you place many pistons, like for example, 4 of them, as in most of the vehicles, you can have 4 cylinders. So around them is cylinders and 4 pistons. And each of this piston and each of the cylinder can be in a different phase. So for example, if the first piston is in the second phase, the third piston can be in the third phase, this can be in the fourth phase, the other can be in the first phase, and so on. So it means that at a given time, at least one of the pistons are going to create, and this is going to happen fast, of course, at least one of the pistons is going to create a force. And this force created by one of the pistons can be used to move the others. So if you design the system correctly or nicely, and usually we also put here a flywheel. So this is just a mass, a rotating mass. So the idea is, once something starts the internal combustion engine, it can continue operating by itself, of course, as long as you supply the fuel, because even if it cannot generate a continuous torque or continuous force, in this case, because the cylinders are going to create just linear motion, a continuous force, if you combine the forces created by the different cylinders, plus if you maybe add here a rotating mass, so that the crankshaft is going to have more or less continuous rotation here in this case, because here we are going to have strokes. So we will have force and no force, force and no force phases. So therefore we may have a very high ripples on the crankshaft. To avoid that, we can just add a rotating mass, and this rotating mass is going to behave like an inductor in an electric circuit, so that the current cannot change fast. In this case, the torque is not going to be able to change fast, this rotating mass going to cause that. Or it can be a capacitor, if you think like an analogy of a voltage, or if you think as an analogy with respect to the current, you can think that it's like an inductor. And here it is the chemical reaction, what is happening. So this oxygen, and we will have the carbon dioxide, some vapor, plus the motion. And on the shaft, we are going to have the rotating motion. And the shaft of the internal combustion engine is going to be connected to a multi-speed gearbox. As you learned, the output of the internal combustion engine, output characteristics of the internal combustion engine will not be proper to be directly connected to the wheels. So therefore, we need a multi-speed gearbox, as we discussed many times. So the more common type of the internal combustion engine is the straight or inline type of the cylinders and the pistons, but we can have many different types. Here I had also the animation, so let me show you the animation. And here this linear motion is going to be going to create a rotating motion, and each of these pistons can have in different strokes, in different phases. They are not in the same phases. But if you put here a high inertia, even if they're in the same phase, maybe the motion can continue just thanks to the inertia. But usually if you design them, you make sure that they operate in different phases. But I think you know it, there are different types of ICEs, internal combustion engines. So they can be 4-cylinder inline, or they can be 3-cylinder inline. Then here the cylinders are going to be, the cylinder phases are going to be shifted by 90 degrees. In a 3-cylinder case, the phases of the cylinder should be shifted by 120 degrees. So we can have the V-type of the cylinders. We can also have the linear type of, not linear, but just horizontal type of the cylinders. One side is on this side, other side is on this side. We can, this is the V6 type of pistons. We are not showing the cylinders, but just the pistons. And maybe you heard that there can be W type and so on. So this name suggests that how the pistons and cylinders are placed and how many of them are going to be there in the internal combustion engine. So what else do I want to talk about here? I think that's it for the internal combustion engine. And I think one of the important things to learn is that it is not able to self-start, not able to self-start. So therefore we use a starter, and which is an electric machine, electric motor, electric starter to start the internal combustion engine. An internal combustion engine is a unidirectional element, so it can just make the conversion from the chemical to mechanical, but it cannot work other way around. So it cannot work in the other direction, it can just operate in one direction. And as we have learned in hybrid electric vehicles, we may have an internal combustion engine if it is not a hydrogen vehicle. And it is in the hybrid electric vehicles, the idea was to make sure that the internal combustion engine is operating at a good efficiency point so that the overall efficiency of the system is high. Next component is the hydrogen fuel cell, and most of the time we simply call it the fuel cell. The name doesn't say much, but the fuel cell is actually the hydrogen fuel cell. The input is going to be the hydrogen, oxygen, and the outputs are going to be the electricity, electron motion, plus the water. Output is going to be the water. So in the hydrogen, it looks actually like the power unit of the battery. The fuel in, and we have actually two fuels, if you want to call like that. The overall reaction is the hydrogen plus oxygen, and output is going to be the water. It literally generates water. And in this case, the input is the hydrogen. It is supplied to the anode part. And the other side, you need to supply oxygen. Most of the time, the oxygen from the air can be used. So therefore, we say that air in. We don't say usually H2 in, but the air in, because we use oxygen in the air directly. So therefore, it is called the air in, and here is the fuel in. and the fuel is the H2. That's coming from the H2 tanks or from the metal hydrides somewhere. So we need to take the fuel. On the anode, we are going to have the separation of hydrogen into H2 ions, H plus ions, and electrons. Here we are going to have an electrolyte, and the electrolyte will allow the passage of the ions, but not the electrons, as in the case of the battery power parts. And the electrons are going to move from the outer connection. And on the other side, we are going to have oxygen plus hydrogen ions and the electrons coming from the external circuits, and it is going to form water. And this can be usually, depending on the temperature of the fuel cell, this can be in the vapor form, or it can be literally the water. Let me write here water. I cannot read it. So this is water. Basically, it can be a little vapor, a little in the liquid form, this water. So if you have a fuel cell vehicle, so fuel cells, usually we call it hybrid electric vehicle because we always need to have a battery. It is going to also have an exhaust. There is going to be exhaust is required for water. So in an internal combustion engine, the exhaust was required to be able to get rid of the remainder of the combustion. So this carbon dioxide, water vapor, and other elements. And in a hydrogen fuel cell electric vehicle, we also need an exhaust where we need to get rid of the water and the water vapor. So if you see a vehicle with no exhaust, it means that it can neither be internal combustion engine vehicle nor a fuel cell vehicle. So it should be a pure battery electric vehicle. So you can just check the exhaust of the vehicles. And so there are different types of the fuel cells. The fuel cells can have different forms and different applications. Usually, we use the proton exchange membrane, or it has also other names, the polymer electrode membrane, but we always have to use the short name of PEM types fuel cells in the vehicles. So as you see, there are different types, maybe even the list is longer, depending on the ion, depending on the operating temperature, and so on. And here it is also due to the membrane. We use this type. So the proton exchange membrane, or other name was written, polymer electron membrane in the vehicles, in the mobile applications. It is used in the vehicles and mobile applications because of, first of all, its low temperature. These high temperatures are used so that we can increase the reaction speeds so that we can get enough power output. But in the vehicles, it is not very useful, this high temperatures, because then you need to have heaters and other components to make sure that you can reach the high temperatures. So therefore, this being low temperature, and it also has a good efficiency, as it will come here. It has a simple structure, solid electrolyte. So the solid electrolyte is easier to handle, and low temperature, it's between 30 and 100 degrees C. So it means that we can get some vapor and some water at the exhaust. High power density, so it has high C and it can give you high power. So therefore, I think in all the vehicle applications, we do use the proton exchange membrane or polymer electron membrane types of fuel cells. In this type of the fuel cells, the PEM, so you will just hear the name PEM. So in one cell, as we have learned for the batteries, these fuel cells are also going to have cell. So therefore the name here is the cell. So we are just looking into one cell, which is going to be extremely narrow. So these are very narrow parts. one side is going to be the anode, the other side is the cathode. Anode is where the electrons are leaving, cathode is where the electrons are going. This is how you can think. And in this case here, we have the electronic membrane, which allows the passage of the H+. Here we need to use a catalyst. Actually, this is one of the biggest problem of the PEM fuel cells. This catalyst, the catalyst is, as we use the platinum, let's call it platinum, as the catalyst. And this is required so that the reaction here in the separation of H+ and E, the electrons, is going to get faster. So we have to use the catalyst in both sides, actually, both in the anode and both in the cathode. So they are not going to take part in the reaction, but they are going to make sure that the reaction is going to be faster. And here we have the gas diffusion layers. The hydrogen is going to be in gas form. The air from air, or the oxygen, is going to be in gas form. So here we are going to have gas diffusion layers. So these gas diffusion layers are a little interesting because this should allow the diffusion of the gas. At the same time, they should also collect the electrons, or they should also supply the electrons. So there should be some conductors and some openings so the gas can diffuse. Then we need to have also the catalyst. So here it explains, so there's a nice website. It explains how the fuel cell operates. So this is a single cell. So here it says this is the anode where the oxygen is, hydrogen is delivered. This is the cathode where the oxygen is delivered. So here you send the hydrogen gas, here you send the air. One important thing is this hydrogen and air should stay separate. So they need to get together in the cathode part once the hydrogen ions are passing through the electrolyte. And the unused there can maybe not all hydrogen is used. There will be some unused hydrogen. We will talk about it. It should be also sent reused because it is very precious. On the other hand, we are going to have water as the output and so on. Here it explains the polymer electrode allows only the positive charge ions to pass through it, the cathode and so on, just similar to the power stage of a battery, which is a very similar idea. The idea is similar. So if we just take a fuel cell, and as we have done for the batteries, we can just check it open its voltage. But now when we talk about the fuel cells, we cannot talk about the SOC, state of charge. We can just talk about the current density because this is just the power conversion part. It's not going to have a state of charge. There is no charge stored in the fuel cell, except for the remaining fuels maybe inside the cathode. And in this anode and cathode, in this case, we also need to look into the cell voltage because we know that these fuel cells, the output is going to be electricity. So assume that there is a black box. Inside, you are going to put some hydrogen and oxygen. Then the output is going to be the electron motion, so the electricity and the water. So it means that if the output is electrical, we may need to have some current density and cell voltage. So the typical characteristics of the PEM fuel cells, they just look like that. You can think it is similar to the open circuit voltage of a battery. So the maximum voltage or the electrochemical voltage of a single cell is around 1.2 volts, 1.18 volts, and so on. It is because of the anode and the cathode material. So the hydrogen, oxygen, the difference, how do we call it? The potential difference between two parts. But we can never reach this 1.2 volts. At the moment that the flow of the ions and electrons starts, we need to have some activation energy for the reactions. So therefore, this power, this voltage immediately drops as you get a demand for more and more currents, because if you demand more currents, then you need more flow of the hydrogen and oxygen, and that requires some extra energy at the electrodes, at the cathode and at the anode side. And as you demand more and more current, the voltage will decrease. So there is a region where we like to use the fuel cell. So for example, maybe in between these two regions, here you can more or less think that we have some voltage source and there is a resistance. And as you demand more current, the voltage that you see at the terminals is going to decrease. So this is more or less the ohmic voltage drop region. And after that, the voltage will drop again quite fast, as also in the batteries, because here we are depleted of one of the gas. So most of the time, maybe the air or the electrons are short of the reactants. As you require more current, it means that the total reaction should be faster, so that the system cannot send so much reactants. So that's why it will decrease. And we would like to typically operate our system in this range, not at very low currents, not at very high currents, and usually in this linear region. And this efficiency of the system is limited. You can never get 100% efficiency. And if you stay within this region where the current density is high, you can operate around maybe 70%, or it depends on the application, and also it depends on the temperature. But there is a maximum efficiency limit that you can reach. And second of all, you cannot operate at the maximum efficiency, but most probably you will operate between 50 and 70% efficiency region to be in a real application. For example, for an electric motor, we can operate more than 95% efficiency, or 90–95% efficiency range. For the fuel cell, so this is the operating temperatures, by the way. So for example, if you go, this is on high, so they say steam product. So this shows here the high operating temperatures. In even low operating temperatures, the efficiency will drop around maybe 50% or so. Of course, you need to ask an expert about it. But compared to the electric machine, which is going to have an efficiency more than 90%, of course, we also need to consider the efficiency. Or actually, no, this is the energy conversion part from, we need to look at the whole efficiency. Let's talk about it later. But what is important is if you have hydrogen and oxygen, and if you need a fuel cell to generate electricity, its efficiency is going to be around 50% and 60%. This is not a very high efficiency system. So a cell is going to have many layers, and we need to supply hydrogen to one side, oxygen to the other side. They shouldn't they shouldn't get in contact with each other, this hydrogen and the oxygen, so that the mechanical system has to be designed very accordingly. If in the cell we can have different challenges, there will be carbon monoxide poisoning. If we have some carbon monoxide coming from the air or from the hydrogen side, there we can have some problems in the membrane. The system can get age quite fast, and the catalyst, the platinum, which is PT, is very expensive, so you need to also recycle it. So the other problem with the fuel cells is you cannot use a cell as in the batteries. A cell can have a voltage around maximum 1.2, but we cannot operate at 1.2 volts or 1.18 volts, it is going to decrease. So it means that to be able to get some voltage output and also some power output, you need to put many stacks in series so that you can get high voltage. In this case, the system is going to compose of many layers, and we call them fuel cell stack because we are stacking the fuel cell. So the small cells are taken and they are stacked together so that we can create a fuel cell stack. So we need to manage the stack, the H2 and O2. You know, in each one stack, we need to supply H2. From the other side, we need to supply O2, and so it should keep changing. Here we are going to have bipolar plates. I think it will come later. Bipolar plate means that from one side you need to supply oxygen, from the other side you need to supply hydrogen, and they need to be separated from each other. Moreover, in each cell we are going to have some water produced. We need to manage the water. The problem with the water is we need some humidity in the electrolyte so that its resistance is low, so it can conduct the ions nicely, but it shouldn't be wet. If it is wet, then it cannot conduct. So therefore, there is a specific humidity of the electrolyte, and we will have some water generated in the cathode. And this water, some part should be used to keep the membrane humid, some part should be sent out from the exhaust. So there is an important thing is the water management. And due to the losses in the system, we need to make sure that the system is cooled nicely. And moreover, it has to be also heated. Because the fuel cells also have a minimum temperature at which they can operate. So for the PAMs, for example, you see that it was given here, it should be operated at 30 degrees to 100 degrees, but usually they will operate in a narrower range, maybe around 50 degrees and so on. So it means that you need to always make sure that the system is going to stay at this temperature range. There is a small temperature range. So since we cannot use the fuel cell, just a single fuel cell, we need to put them in a stack. Since we stack them, we call them a fuel cell stack. And this fuel cell stack has to be somehow managed by a system. And with all the hydrogen supplies and also the thermal managements, ventilations, and so on, we call it a system. Then it becomes a fuel cell system. To a fuel cell stack, we need to have H2. So usually the H2 is stored in the high pressurized tanks. So therefore, if we just put a valve, then we can have a good H2 supply to the fuel cell. The air, usually we need to, I think it will come in one of the next slides. So the air is directly taken. So, but its pressure is not enough. So we need to add here a compressor so that the air is also compressed. It has a high pressure, so the reaction will be fast. We can just reuse some of the hydrogen for if the unused hydrogen, it is recycling. We are going to have water as an output. We are going to have waste heat from here. And we also need to control the system in terms of the temperature and the humidity. We need to control the humidity within the fuel cell plus the temperature of the fuel cell. And when we talk about the stack, there's, as we discussed, Toyota Mirai is one of the most famous fuel cell vehicles. So in the newer versions, they don't have the humidifier outside to keep the membrane at a given humidity, but they just have some internal circulation. Here you see the reuse of the hydrogen. Hydrogen is reused. The hydrogen comes from the 700 bar pressurized tanks. Then with the valve, you can control the hydrogen flow rate. And of course, depending on how much power you want at the outside, you need to control the flows, hydrogen flow and the air flow. So therefore here it is controlled, H2 flow is controlled. And here you can see that the air is taken out. This is the exhaust. Exhaust gas is going to be the water vapor and water. And thinner membrane, actually the membranes are quite thin in nanometers, I suppose. So you need to put many of them in a stack. In the other one, there will be some examples. How many cells do we have? So they used to have 200 cells times 2, so 400 cells. Now they, in the newer versions, it is also quite a little old, 2014 version, they have 370 cells. I just wanted to put here the numbers so that you have an idea, so how many of them you need in a stack and why do we call it a stack. So we have fuel cells, then we put them together, then we have a fuel cell stack. And with the management, the extra management, we have the system, fuel cell. They're all fuel cell. Anyway, cell is here, fuel cell stack and fuel cell system. Maybe I just delete this cell. And here you see the 90 kilowatts, 114 kilowatts, and volumetric power density, number of cells, thickness of cells. Here it is given 1.68 millimeters. So this is the whole cell with everything. And now they have a smaller cell. It means that the anode, cathode, electrode, diffusion layers or catalysts, and also the thermal management, everything of a cell is going to be less than 2 millimeter, within less than 2 millimeter thickness. So in a fuel cell, the whole energy is going to come from the fuel cell stack. So even it's a hybrid electric vehicle, if it is not a plug-in electric vehicle, we know that the whole energy is going to, for example, assume that we have hydrogen tanks. We store the hydrogen in the hydrogen tanks, and we are going to get the air from the, oxygen from the air. And to be able to have a high pressure oxygen, we also need to have compressor. And these compressors can be also quite high power. They can be up to 10 kilowatts. So the compression, so that the pressure of air is high enough to get a good chemical reaction. The compressors, they are usually a high-speed electric drive system. And this is going to be the input of the fuel cell system. And the output is going to be the voltage and the currents. Of course, here I'm going to see voltage and I'm going to see a current. So the problem of the voltage and the current is the voltage is going to depend on the currents, and also it's going to depend on the flow rates. Plus, it is going to depend on the temperature and humidity within the fuel cell system. Moreover, the system is going to get affected by the pressure and the outside. For example, if you go up on the mountains, or if you are in the valley, you are going to have a different air pressure, and it is going to change the oxygen flow rate. So that's why the temperature is important. The atmospheric pressure is important coming from outside. And also the humidity is important because the system needs to operate at a given humidity for its operation. So as you see, it is a system which requires the control of gas flow, which require temperature control, pressure control, and humidity control. And the voltage and the current of the system is going to depend on all of those. So therefore, we can say that, and this is usually unidirectional. So here it can just operate in that direction. It can maybe operate a little in the reverse direction. So you can also use the system to create some hydrogen, but I think it's not efficient in the other direction. So this is the air inlet, let's say like that, in just unidirectional system. And it is not a very fast system. So if you want to change the current, so you need to first make sure that the gas flow is controlled and so on. So you can think that the system is not the fastest one. So therefore, actually, in most of the fuel cell vehicles, we will also use a battery. And the battery will be kind of the part which is used to supply the power, because this is good for the energy. But if you demand power as high power or low power from the fuel cell system, then the fuel cell system is not really capable of doing that. So that we can use the battery to store the excess energy coming from the fuel cell, and also to supply the excess energy which is required, for example, during acceleration. So this is going to it is going to balance the power requirements. So the battery will be used for the power requirements. So for also the fuel cell system cannot self-start, because as you see here, we need to have air compressor, we need to have temperature management, pressure management, and so on. The fuel cell system is going to need the battery to be started. So fuel cell system needs battery to start, and fuel cell system needs battery for high power demand. And the last one, if you have a fuel cell system, needs battery for regenerative braking. Because the fuel cell cannot accept the power, but the battery can operate unidirectionally, bidirectionally. So that if you want to do regenerative braking, you also have to have a battery in the fuel cell systems. So long story short, the fuel cell systems always come with a battery. So the result, FC vehicles always have a battery pack. It won't be a very high battery for the storage. It will be around some few kilowatt hours. So let's say 1 to 2 kilowatt hours, because it is just there to balance the power requirements and just do the regenerative braking. So therefore, since they will always come with a battery pack, which is not super big, we usually call them fuel cell hybrid electric vehicles. So you can always use the word hybrid with the fuel cell, because we need to always have a battery. Or even if it is said that it is a fuel cell electric vehicle, usually we do have an H, it means the same. There should be always a battery to be able to control the fuel cell system, to be able to compensate the power demand, because this cannot react fast, and moreover, to be able to do regenerative braking. So maybe this is very, very important. Okay, so let's stop here for the first lecture, first hour, and have a break. Let me pause Zoom recording. Okay, let's correct that regarding to fuel cell efficiency. So I said that the fuel cell may be operating at 50% efficiency. So first of all, this is most from a high temperature fuel cell, but I guess this result is, so for a cell, 70% efficiency is okay. But in the fuel cell stack level, and of course, if we also add the other energy converters, the fuel cell vehicles are going to have an efficiency. The whole vehicle is going to have an overall efficiency around 50%. So 50% efficiency of a fuel cell vehicle. So which is going to be much less than the battery electric vehicle. So you can assume that is 80% of a battery electric vehicle, and it is around 25 to 30% for internal combustion engine vehicle. So it means that the fuel cell vehicles are kind of intermediate step. The advantage of the battery electric vehicle is high efficiency, but low range. Low range is its minus, and this is going to be long range, but low efficiency. So the fuel cell electric vehicles are just in between that. They have a medium range and medium efficiency. So therefore they were famous for some time. So the other energy converter is the electric machines. We are going to spend some weeks on the electric machines. I just want to give an overview on the electric machines. So the electric machines are actually bidirectional. So if you supply electrical power, they can convert it to the mechanical, and in this case we call them motors. And if we just do it other way around, if we supply mechanical power and get the electrical power, then they are going to operate as a generator. So actually we have different types, and we can just divide them into 4 parts. The first part is the rotor is going to be round, stator is going to be round. And in this case, if we don't have any saliency, we don't have any reluctance torque or the saliency torque. So these are just going to create the electromagnetic torque. So in this case, the electromagnetic torque, you can just imagine due to 2 fields try to catch each other. So the stator here, it is just shown with a winding. For example, if stator is excited like that, it is going to create a field. Of course, it's going to be different. We will discuss about that. So it is going to create a magnetic field in this direction due to the stator, and the rotor has the magnetic field in this direction, FR. So I just used the right-hand rule. What I know is stator is going to have a 3-phase winding, and the stator field is going to rotate. So the stator is going to have a rotating field. So the magnetic field created by the stator is going to rotate so that the rotor will try to catch it. Then this is the motor operation. If the rotor tries to catch the stator, this is the motoring operation. If rotor was ahead of the stator, and if the stator is trying to catch it, then it is a generator operation. And if we have just this effect, the stator field and the rotor field effect, then we are just going to have the electromagnetic torque. The torque due to the fact that these 2 fields try to align. You can think what I just explained here as one magnet here, which is in this direction, another magnet here, which is showing another direction. And of course, if you can just move this magnet due to the stator field, this other magnet will try to catch it. So this is just this effect. In a way, if in an electric machine, if you have just this effect, it is the electromagnetic torque. In addition to the electromagnetic torque, you can have also some reluctance torque. Reluctance torque means that even if you have just one field, for example, in this case, just the stator field, Fs, created by those windings, and the rotor is not excited, here the currents are 0. What I know is even if Fr is 0 in this configuration, for example, for Fr being 0, no field, so there's nothing I supply here, I know that this rotor will try to align itself with the stator field because of the reluctance. The magnetic materials are good conductors of the magnetic field. So therefore, the system will try to reduce its energy state and the energy or the length of the magnetic fields. So this Fs is going to travel something like that. Half from this side, other half is going to go from this side. So if this rotates, the length of the magnetic field is going to be shortened. So therefore it is going to rotate. So this red path, even if Fr is 0, is the reluctance torque. And if you have the saliency in the rotor, here it is not magnetically round, or saliency in the stator, or saliency in the boat, you can also have the reluctance torque. If you have the excitation in the stator and the rotor, the excitation can be wire by the coils or by permanent magnets. You are going to have always the electromagnetic torque. So it means that for that you need to have Fr and for sure, and F, I just put the other way around. To get the electromagnetic torque, you need the first all stator excitation plus the rotor excitation. So you have no other chance. You need to have both of them. So they are and. To get the reluctance torque, you need to have just stator excitation and no rotor excitation. Also, only the rotor excitation. So this is not a force or torque created by both of them, but just with one of them. So, and it is caused by the stator flux plus the saliency in the rotor. Or in this case, it can be due to the rotor flux and saliency in the stator. And here, both of them. So one of them has to be there. I will talk about it more in detail in the upcoming weeks. And so all the machines that we know so far can be categorized as one of those configurations. Those are all just representative electric machines. In this case, if we have no magnetic saliency, the most common ones that we know are the induction machines, are round rotor synchronous machines, or surface mount permanent magnet machines. The first one, where we have just the mutual torque or the electromagnetic torque. Let's also call it mutual torque, because we need to have both fields and they mutually creating some torque. This second ones, and they are all very famous machines, so they are highly used in many applications. The B is going to be the single saliency and interior permanent magnet machines. These are very, very important for electric vehicles, as I will show in upcoming slides. Most of the electric vehicles do have interior permanent magnet synchronous machines. They can be also synchronous reluctance machines and salient pole synchronous machines. This was round, this was salient, the same configuration. And this configuration, what is this configuration? Who remembers that? I didn't explain C, so this is B. This is A. What is C? Any example for the C? Parisa, are you talking? We cannot hear.
No, I'm not talking.
What is this, Parisa? Okay, I ask you. So there is field winding, which is DC. There is armature, which rotates inside. There are some brushes. What is this configuration?
I don't remember really. My mind doesn't work at this time of the day.
Okay, let me draw it for you. So we have field winding. Then we have armature. In the armature, we have armature winding. And we put here some brushes. Does it look like C, what I have drawn here?
Yes.
What is this machine?
Is it?
It is a DC
Is it
machine.
DC?
Yes,
Yeah.
exactly. This is the DC machine. So here, this is a DC machine. I didn't put it here because we don't use DC machines in electric vehicles because of the brushes and because of some other reasons that we cannot really control them if we use permanent magnets and so on. And the doubly salient machines are the switch reluctance machines, but switch reluctance machines, not exactly this. They don't have any FR being 0. There is no machine which has double saliency plus FS and FR. There is nothing like that. In the it's just the FR being 0 is going to give me the switched reluctance machine. So the machines can be categorized like the stationary field DC machines, rotating field, synchronous and asynchronous machines, and switched field, which are the salient pole machines. There are also other types like transversal flux, axial flux, radial flux, and so on, which doesn't matter much. So for the electric vehicles, we don't use DC machines. We usually use rotating field machines. And from the rotating field machines, we use either synchronous machines or asynchronous machines. From the synchronous machines, we use squirrel cage rotor with copper rotor machines for the EVs. But this is in some examples. In other examples, we do use salient pole PM excited. So PM excited, sinusoidal excitation, and maybe PM excited, electrically excited salient pole. Here, maybe I just write here salient pole PM excited. So in most of the applications, we use salient pole PM excited electric machines, which are IPM SM. So here you can see an IPM SM. This is the most used type of the motor in an electric vehicle. And the second is the induction motor. As I will discuss in the next week, we will also show in which direction the trend is going. But for now, almost 90% of the vehicles have an IPMSM, and maybe 10% have the induction machines. And some few vehicles are having synchronous machine with electrical excitation. So maybe that can be seen as a trend. And some vehicles try to get rid of the permanent magnets. So if just want to see some of the vehicles, electric machines, so stators are boring. The stators just look the same. So here there are no stators. We are just looking into the rotors, because if you have the rotating field machine, they have all the same stator. So stator is same for all. And it usually is a round stator. For example, what you see, I had pictures, but I deleted them just today. So the stators are here. So for example, all these machines have the same stator. So the outside, this part is the stator. And they just have some openings for the windings. Windings are placed in the stator, and we usually use a 3-phase stator. For example, for an IPM motor, stator just looks like that. For induction motor, let's put it like that. For an induction motor, we can use the same stator. So for the rotating field machines, there are different stator options, of course, but more or less you can use the same stator for all of them. So here you see that the electric machines in some of the electric vehicles, and all of them are IPMSMs, so interior permanent magnet synchronous machines. So they are all IPM SM. SM stands for the synchronous machine. PM stands for rotor is excited with the permanent magnets. Interior, the I stands for that the magnets are inside. So these are all the magnets which are buried in the rotor. So these are interior permanent magnet synchronous machines. And at the moment that you place a permanent magnet in the rotor, the machine can only operate as a synchronous machine. So there is no permanent magnet induction machine. So it has to be a synchronous machine. As you see here, the previous older machines and newer machines, they have permanent magnets. Ford, Nissan Leaf, Toyota Camry, Honda, Chevy, they always use magnets, and they are almost all of them uses buried magnets, so interior permanent magnets. So therefore, this is what we will be covering in the next week's interior permanent magnet machines. And here there is an overview of the machine types of the vehicles. So the Tesla Model Y, Tesla Model Y rear and front, so that they have different housings. Jaguar I-PACE, this is also IPMSM machine, Nissan Leaf. Audi e-tron, this has to be an induction machine, front and rear, or one of them at least has to be induction machine. The others, Model 3 machines, Chevy Volt, Toyota Prius, Chevy Bolt, and BM3, they should be the IPMSM machines. So one or two of them are the induction machines. Maybe one of them are induction machines. I don't know which one. And you cannot tell it from just by looking here. You need to see their rotors, but most of the machines are going to have in this IPMSM type, the others are going to be the induction type, and they're all three-phase. Maybe this is very commonly seen. So three-phase machine, three-phase, three-phase, three-phase. All of them are three-phase. These are the supply connections. So here there are four phases. Maybe it is the Y connection. So the neutral point is taken out. Maybe it's some other connection, I don't know. Also three-phase machines. So in the next 2 weeks, we will be completely talking about the electric machines, and we will usually talk about the salient pole PM excited IPMSM machines, a little about the induction machines, and if we have time, we can also talk about the future trends in which type of machines are getting more popular in an electric vehicle. Okay, so this was the electric machine introduction. The next energy converter is going to be the DC-DC converters. On board, we are going to have DC-DC, AC-DC, and also DC-AC converters, all type of converters. Maybe I just start writing with an overview. We are going to have, maybe let's start from AC. We are going to have AC to DC converters, DC to DC converters, and DC to AC converters. Before I show you my slides, so in the slides I kind of explain it. What can be an example for the AC-DC converter? Any idea? On board.
Bridge rectifier and a capacitor.
Bridge rectifier and capacitor. Okay, perfect. This is a rectifier. So for which purpose do we use it? Why do I have it on board?
Maybe to charge the battery.
Perfect. So these are the chargers. So if you want to charge the battery from an AC system, this is what you can use. Okay, an example for the DC-AC, maybe.
Again, power from battery to electric machine vehicle.
So this is the from battery traction, okay, from battery to electric machine. And how do we call this inverter? This is usually called the traction inverter. And so of course this other way around, if I have the DC AC and these are the bidirectional systems, it can also convert it from AC to DC, and this can be also an example, right? If the machine is operating as a generator, and then the AC is converted to the DC. And here we have to use an inverter for the traction drives because we have a three-phase AC machine as a common traction motor. So therefore, if we had a DC machine as the traction motor, of course, we didn't require a DC AC, but since we have a three-phase AC machine, so both IPMSM and induction motor, they are three-phase AC machines. They are both AC machines. So therefore, we need the inverter. And for example, an example for DC to AC, usually these are unidirectional, just to charge the batteries. We don't want to charge the AC system if we don't have the vehicle to grid application, of course. So in this case, an example for the DC-DC conversion. Any example?
Buck, boost, some kind of converters.
Okay. Buck, boost. What could be the use of buck boost converter on board?
I think to adjust the voltage or current between this AC to DC or DC to AC.
Mm-hmm. Oh, so this is adjust
A kind
voltage
of interface.
level. Mm-hmm. So it can be first, I will just say it actually, this is perfect. It is, we need to adjust the voltage levels. And Ali also tries to say that we need to connect different sources together, connect voltage sources, let's say, together. Forces together. Okay, perfect. So I will start with DC-DC converter. I don't know why, but the first part we will talk about the DC-DC converters. So as we just mentioned, the DC-DC converter can be used a buck type or a boost type. It is main usage of the DC-DC converter is to boost the DC link voltage, or also to stabilize the DC link voltage. For example, if you directly, for a battery electric vehicle, so assume that this is a battery, this is the output terminals, you can place here a DC link, and after that you can drive the three-phase motor by using an inverter. So this is a three-phase motor. And in this case, this battery voltage here is going to fluctuate, because we know that the battery voltage depends on the SOC of the battery, FSOC, and also in the current of the battery, and it depends on the current of the battery. And if we place directly here after the battery boost converter as here, first, it is used just to increase the voltage. Second, it can stabilize the voltage. So increase the voltage, plus it can stabilize the voltage as the battery voltage changes. So we usually use the boost converters because we tend to have a higher voltage levels for the motors and the generators, so that the motor current is decreasing. So we want to have a high voltage motor to be able to have a less current in the motor, because the size of the motor is more or less related to the current that you need to supply. So it means that if you increase the voltage of the motor, for the same power, you can decrease the size of the motor. So therefore, actually, there is a trend to have a high level of DC bus voltages, and we can use a boost converter to increase the voltage level. So one disadvantage of using here the boost converter is you are putting a controlled circuit between the motor and the battery, between the generator and the battery, so that actually here you may cause some speed-related problems, because you are just limiting the speed of the energy conversion between battery and the motor. If motor is braking, regeneratively braking, and if power has to be sent to the battery, if it is directly connected, you can directly send the power to the battery. And the battery, you can think like a infinite sink, even if it ages, even if we don't want to send it high currents or ask for high currents, battery can accept high currents for a very short time. At the moment that you put here a boost converter, you can control the battery current much better, so it is good for the battery. But the charge flow from one side to other side is kind of limited. This speed is limited with the control of the boost converter. So first thing is the boost converter. We may also need a buck converter. If we have a high voltage from the battery and we need a low voltage, then maybe we need to use a buck converter, but it's not common. If you use a DC-DC converter in a battery electric vehicle or hybrid electric vehicle after the battery, it is usually the boost type because we want to get a higher voltage in most of the applications. That was the first one. Then the second one is the connection of two electric power sources. So in the previous one, that was used for a hybrid electric vehicle, the Prius, but in the Prius, we had just one battery. So here we had one battery and we have generator or motor in the Prius case. So we didn't have any additional electric source. So we had just one electric source. But there can be vehicles where we have two electric power sources, two or more. One example is the fuel cell system. In a fuel cell system, the fuel cell always comes with a battery. This can be for the fuel cell vehicles, and this can be also for the vehicles with supercapacitors. Anyway, it is already written, so I don't need to take notes. So fuel cell stack plus the battery and supercapacitors. So if you have two electric power sources, so actually maybe the first option looks like that you can connect them together directly to the same DC bus, so the fuel cell and the battery. But the problem is we shouldn't connect two voltage sources in parallel if their voltages are not same. Otherwise, we will have some currents between those components, and this is something that we really don't like. And as you know, the fuel cell, as we have just discussed, the current is really not controlled nicely. So it has its own speeds, this fuel cell system. So therefore, this is not good. We wouldn't apply this, but we need to put at least one DC-DC converter so that this DC link bus voltage is controlled. For example, if the battery is operating at 350 volts, this DC-DC link voltage, DC-DC converter, will adjust any voltage from this side. Assume that at this point it is 200 volts. It is going to change with time. And of course, this is also going to change. But we can measure the DC link voltage. We can measure the fuel cell system voltage. And we can just adjust the other side of the DC-DC converter to be 350 volts. So if you want to connect two electrical power sources, it is a good idea to use a DC-DC converter, at least one of it. So you have the option to put the DC-DC converter after the fuel cell stack or after the battery system. So you have two options for the DC-DC converters. If you put the DC-DC converter after the fuel cell stack, it is enough if it is unidirectional. Because I know that the fuel cell system is not going to be used for regenerative braking. It's not going to accept any power from the inverter. But if you put it in after the battery, it should be a bidirectional type. And it's done. If you put it after the battery, it should be bidirectional because the battery is going to supply power and also it's going to accept power in our system. So that's why it should be bidirectional type. Or another option is you can put both after both of them a DC-DC converter. And if you have also an ultracapacitor or supercapacitor, you can put converters after everything, converters just after one, after two of them. At least you need to use two converters. And most of the time we like to have a converter after the ultracapacitor. Okay, you are given such a system, fuel cell system with the battery. And you don't want to use two DC-DC converters. Which configuration would you choose? The configuration in B or configuration in C? Would you put the DC-DC converter after the fuel cell or would you put it after the battery? Any comments?
After the fuel cell, I think.
Okay, again, why?
Because it's unidirectional.
It's simpler, yes.
Yes.
And then you look into the dynamics of the fuel cell and the battery. So this is a relatively small, it is a, you know, the current of the fuel cell is hard to change. And this is, so actually there is one disadvantage if you put the DC-DC converter here. In a fuel cell vehicle, this fuel cell system is the main energy source, right? So they look at the same size here. In this paper, it is shown like that. But the battery system is going to be 2 kilowatts, 2 kilowatt hours. So it's a small system. So the fuel cell is going to be the bigger part. So the whole energy is going to come from the fuel cell. So the whole traction power, which is required to drive the electric power, is going to come from the fuel cell. So if you put the DC-DC converter after the fuel cell, you need to use a unidirectional fuel cell, but it is going to be on the path of the energy flow, the main energy path, because if it is not a plug-in vehicle, the whole energy used by the system has to come from the fuel cell. So that's going to be a negative effect if you put the DC-DC converter after the fuel cell, because this is the main energy path in a fuel cell vehicle. Main energy path. But on the other hand, as just Ogün said, it is going to be a unidirectional system. And on the other hand, it's you know, for if you do the regenerative braking, you won't have any DC-DC converter on the path, because this DC-DC converter for the regenerative braking, you need to make it quite fast to be able to accept all the power immediately. So you can put it here or there, as depending on the application. But if you put the DC-DC converter after the battery system, so this DC link voltage is going to fluctuate a lot. The battery voltage is fluctuating, but not fluctuating as much as the fuel cell voltage. So therefore, if you choose to put your DC-DC converter to the battery side, you accept that the DC bus is going to have a more fluctuating voltage because of the characteristics of the system. Okay, and if you want to put two converters, this is also possible. In this case, the one of the converters has to be controlling the voltage and the other one has to be controlling the currents, because you don't want to control the voltage, DC link voltage from both sides. Otherwise, you will have a problem. So usually the fuel cell system is controlling the DC link current and the battery system is controlling the DC link voltage. Otherwise, you have one controlled parameter and two controllers. So it is not a good control system. So therefore, if you have two converters, you need to control them in different modes. And for the ultra capacitors, I said that you usually need to add a DC-DC converter. Why do I need to add a DC-DC converter after an ultra capacitor? Do you remember we discussed it actually earlier? In an ultra capacitor, the stored power or energy is 1/2 CV square. So it means that to be able to get the energy out of the ultra capacitor, you need to apply a high delta V. So you need to, if you want to get the energy out, voltage is going to decrease. This is what a capacitor does. So it means that if you let the voltage of the ultra capacitor to be same as the DC link voltage, you can just get a little of the power stored in the ultra capacitor. To be able to use the whole power, you need to make sure that here you have a boost type power converter. So even if the DC link voltage is constant, the ultra capacitor voltage can go to very low values so that you can use the more power from the ultra capacitor. So I mean, so depend, if you have multiple sources, then you have to use, if you have two, at least you have to use one. Otherwise, you cannot connect them. If you have three, at least you need to use two, or maybe you can omit it, but you will have some circulating currents between charging currents between the systems. To have a charging current between the battery and the ultracapacitor is not a bad thing. This is actually something that we want. But the problem would be that the ultracapacitor is going to be governed by the DC link voltage, so you cannot get the energy out, the required energy out from the ultracapacitor. That can be a disadvantage. But if you have a fuel cell plus battery system, you don't want to have currents, you can't have currents going to the fuel cell. So you have to use at least one DC-DC converter. So DC-DC to boost the voltage or to connect at least two of the power sources, we need to have DC-DC converter at the DC link. And the third usage of a DC-DC converter is we all have them in all the electric vehicles. We want to have a buck converter to charge the batteries, so to charge the low voltage batteries. So here we have the high voltage side. Assume it is 200 volts or 350 volts, as we discussed earlier. They're around 300 volts. The high voltage bus battery. And we also have the 12-volt battery. So these are the regular batteries, regular car batteries, and maybe they can be now 24 volts in some vehicles. We also need to charge those charge batteries. But now we don't have the starter generator in an internal combustion engine. We will have a starter generator or generator part to charge these 12-volt batteries. But in a battery electric vehicle or fuel cell vehicle, we don't have this generator to charge the 12-volt batteries. And this 12-volt batteries is required for the regular loads on the vehicle, for AC in some vehicles, for the lights, for the other automatic systems, for the steering and so on. We need this 12-volt battery to 12-volt battery, and we cannot directly charge it from the wheels as we had the generator, the small electric machine in internal combustion engine vehicles, but we need to charge it from the high voltage battery. And to that, we need to have a buck converter because it's around 200, this is around 200 volts, this is 20 volts. And by regulation, they have to be isolated because this is not a dangerous voltage level. This is a dangerous voltage level. So therefore, this has to be isolated type of buck converter. Okay. So that's the third application. This is power is not going to be high, and usually they are unidirectional. So you just want to charge the 12-volt battery, but there are some applications where I think they are bidirectional. So, but you have to have such a DC-DC converter also on board to be able to charge the low voltage battery. We cannot just get rid of the low voltage battery. Okay. So this will be quite fast. Let me also finish the inverters. As you said, we are going to also have the inverters, DC, AC, and they're also going to operate in the rectification mode too. And the inverters are used as the motor drive. So they are the traction inverter. Let's call it like that. Traction inverter. Since the machines are three-phase, the inverters are also going to be three-phase voltage source inverters. Three-phase voltage source inverters are going to be used, and they are just going to be very close to the electric machine. So as you see, this is the inverter. And instead of having an internal combustion engine, we are going to have an inverter plus an electric machine in our vehicles. So the motor, the inverters, the numbers can be different. If we have multiple traction motors, we need to have multiple inverters. Or for example, for a Toyota Prius, we had one generator and one motor, GM1 and GM2. So you need two inverters for both of them. So as the number of the electric machines, generators and motor increase on board, then you need to have multiple inverters. And there's an example here. This is written, okay, I deleted it, I guess. This is, I think, Honda. This should be from here. It's written Honda Accord, and it is a hybrid electric vehicle. It has both the generator and the motor. So they have just combined the inverter for the generator. It is a lower power than the motor. Inverter for the motor. Plus, it has also a boost converter. So this is the boost converter part. This is the motor inverter, and this is the generator inverter. It has the motor, generator, and the gear. As you know, we also need to use a gear in an electric vehicle. They are put in the same housing, and also as the inverter, they are also put in the same housing. And in all the inverters, we have to use a DC link capacitor. And for example, here they said that before the boost, 370 volts DC, and a boost, a DC link capacitor of 400 microfarads. And at the boosted part, where the 700 volt DC, they use a DC link of more than 1,000 microfarads of capacitor. So if you have more motors or generators, then we need to have different so many inverters in the system. And the inverter is usually a little more expensive than the motor. And this is also one of the very important components of the electric vehicle. The last one of the converters is the charger. So this is going to be this one for the charger. Let's put it 3 with the order. And this chargers is we have like onboard chargers, and this onboard chargers, if you connect to an AC voltage, a single phase AC voltage, you need to be able to charge the batteries. And again, they are also with a galvanic isolation here, as you see. It has a rectification stage, power factor correction stage. Then to be able to have the resonance, here is the H bridge to invert to change the frequency to a high frequency. Here is the transformer, and here is the rectification stage. So as we were discussing in the previous weeks, if you want to charge a battery, a lithium-ion battery, you can operate the charger at constant voltage and constant current modes. So as the battery SOC is low, you want to charge the battery with a constant current so that the battery is charged quite fast. So it is at low SOCs. But once the battery reaches a high SOC, you don't want to charge the battery with constant currents, but you want to decrease the currents of the battery so that you stay with the constant voltage charging. And in this case, the current will decrease automatically because your battery is getting close to the full. It has a high voltage, and you keep the voltage constant at a given value so that your current is limited. So this is applied at high SOCs, so that to limit current. So this is applied at low SOCs to get fast charging. And these chargers should be able to do that. It's both constant voltage charging and constant current charging. So this is what you see from so this is what you connect to your circuit, to your vehicle, and this is what your charger is doing. So we will also talk a little more about chargers later. But the fast chargers are not going to be inside the inside on board. So these are just what we have on the board. The fast chargers are going to be outside of the system. The DC-DC converters are going to be not on the board. Okay, so we can just stop here, and on next Tuesday, I will start with I will finish this mechanical converters. We will talk about the differential and this gearbox a little And you already know the two types of mechanical converters, which was the speed couplers and torque couplers. I'm not going to discuss them again, but we just maybe mention them one more time. And we will try to have a look at the operation of a differential a little closely. It won't take long. Then we will start with the overview of the electric motors in electric vehicles. Okay, that's it for today. So do you have any questions?
Hocam benim dersim